Welcome to another episode. Before we begin, I'd love to know something simple from you. Share in the comments where in the world you are right now and what time it is as you're listening. It's always fascinating to see these stories ripple across time zones, weaving together nights, mornings, and quiet in between hours. And if you'd like to hear more journeys like this one, consider subscribing. It helps this calm little space continue to grow. Tonight, we turn our gaze towards something that almost defies imagination, a place where light itself disappears, leaving behind not brightness, but a shadow. For centuries, black holes lived only in equations, thought experiments, and speculation. They were the monsters at the edge of physics, invisible by definition, unknowable by design. And yet, in 2019, humanity achieved something extraordinary. We took a picture of what cannot be seen, a photograph of darkness itself, framed by light bent through gravity, revealing the shadow of a black hole at the heart of another galaxy. This is the story of how we learn to capture the unseeable, a story of physics and persistence, of telescopes scattered across deserts and mountaintops, of data stitched together across the earth, and also a story about ourselves, our relentless urge to look into the abyss and to return with proof. So, if you're ready, let's begin. It is one of the strangest pursuits in science, to take a photograph of something that does not emit light, a photograph of darkness. At first, the very idea sounds absurd, almost like a riddle wrapped in contradiction. Photographs, after all, are built on light, on photons striking a surface, triggering reactions in chemicals or electronics, leaving behind a trace of brightness. Remove the light, and you remove the very medium that makes photography possible. Yet this impossibility is precisely what makes the shadow of a black hole so compelling. To understand why this paradox exists, imagine standing in a dark room at midnight. The furniture, the walls, the shapes around you, all of them are still there, but without light you cannot see them. If someone were to take a picture, the camera would faithfully record nothing, a flat plane of blackness. In this sense, a black hole seems like the ultimate dark room, a region of space-time so intense that light itself cannot escape. But here the analogy breaks down, because unlike a room in shadow, where light can return once you open a window, the darkness of a black hole is permanent, absolute, woven into the geometry of space-time itself. It would be tempting to say that such a thing is forever invisible, hidden beyond the reach of human senses. And for much of scientific history, that was the assumption. When John Michell, an English natural philosopher, wrote in 1783 about the possibility of dark stars so massive that even light could not escape, his idea was treated as a curiosity rather than a serious proposal. Without any way to observe such objects, what use was there in discussing them? The thought remained a kind of speculative ghost in the margins of physics. And yet, absence, it turns out, can be as revealing as presence. Shadows tell stories. When you see a shadow on the ground, you are not seeing the object itself. You are seeing light's refusal to pass through. The darkness is a negative imprint, a mark left by the obstruction of brightness. In the same way, the shadow of a black hole is not the object itself, not the singularity, not the horizon, but the boundary where photons disappear, where space-time bends their paths inward and refuses to let them return. This is a strange kind of vision. To see a black hole means to see what is missing, to trace the outline of absence. The first great paradox is that this absence is brighter than anything else. Around the black hole, matter spirals inward at nearly the speed of light, heating to millions of degrees, glowing in radio and X-ray wavelengths. Jets of plasma shoot outward across thousands of light years. Against this backdrop of furious light, the whole appears as a void, a circular patch of darkness, a missing piece of the cosmos. The shadow is not just blackness, it is contrast. the edge of nothingness against a sea of something. If there is a poetry to science, this is one of its most haunting verses. That the universe can reveal itself through silence, that emptiness can be as eloquent as substance. The event horizon is mute, but its muteness has edges, and those edges can be traced. The camera does not capture the black hole directly. It captures the refusal of light to emerge, the cosmic veto written in photons that never return. But even this poetic framing doesn't fully solve the puzzle. For to take such a picture, one must ask, what scale of shadow are we speaking of? The black hole at the center of our galaxy, Sagittarius A star, is about 26,000 light-years away. Its event horizon spans about 25 million kilometers, enormous by human standards. Yet from Earth, it appears smaller than a donut sitting on the surface of the moon. That is the size of its shadow in our sky, a fraction of an arc-second, impossibly tiny, blurred further by the turbulence of interstellar gas. Imagine trying to photograph a grain of sand in New York while standing in Paris. That is the challenge astronomers set themselves, and still the paradox grows deeper. What does it even mean to photograph something that can never be illuminated? A normal photograph is a play of reflections, light bouncing from object to camera. But the shadow of a black hole is a one-way trap. Light does not bounce. It falls inward and never returns. So instead of recording reflection, astronomers record deflection. They measure the tortured arcs of light as it bends around the hole, mapping the place where those arcs vanish into darkness. The image is not of the black hole, but of the stage it sets for surrounding matter. It is less a portrait than a silhouette, drawn in negative space. This inversion, seeing by not seeing, is strangely fitting for our species. Humans have always peered into darkness and tried to interpret what is hidden. The earliest astronomers traced shapes in constellations, inventing mythologies from patches of night sky. Cave painters used shadows from flickering firelight to imagine animals that were not there. Even in everyday life, we are experts at noticing absence, the missing seat at a table, the silence where a voice should be. Perhaps it is no surprise, then, that we have extended this instinct to the cosmos, turning a black hole's refusal to shine into a kind of cosmic mirror. There is also something deeply humbling in this paradox. To photograph a black hole, scientists had to combine telescopes scattered across the planet, synchronize atomic clocks to a fraction of a billionth of a second, and gather petabytes of data that no single human eye could ever pass. All this machinery, all this global cooperation, to glimpse a ring of light surrounding a void. It is as if the universe is reminding us, to see what is truly hidden, you must listen carefully, work patiently, and accept that some of the most profound revelations arrive not in what is given, but in what is withheld. The shadow of a black hole is not just an astronomical object, it is a philosophical invitation. It forces us to reconsider what it means to see. Is vision only about photons bouncing into our eyes, or can it also be about the shapes left behind when light is removed? Can absence be a kind of presence? The black hole answers with a resounding yes. In 2019, when the Event Horizon Telescope team released their image of the black hole in galaxy M87, reactions around the world were tinged with awe and disbelief. Some said it looked like a cosmic eye, others compared it to a halo of fire. But perhaps the truest description is the simplest. It was a shadow cast not on a wall or a floor, but on the very fabric of space-time. And just as the shadows in our daily lives remind us of the objects that block the sun, this cosmic shadow reminded us of something larger, that even in absence, reality makes itself known. It is worth pausing here before we rush into the details of telescopes and algorithms to sit with this paradox. Imagine yourself at the edge of an abyss. The darkness is total, but around it swirls light. bending and twisting as if reluctant to fall. You cannot step inside, but you can see where the universe draws its boundary. That boundary, neither object nor illusion, but something in between, is what we have photographed. The image, then, is less about seeing a black hole and more about learning to see differently. It is a reminder that science is not always about capturing what is directly visible. Sometimes it is about learning to read the silence between the notes, the gap between the stars, the circle of nothing framed by everything. And in that silence, there is beauty. When we look back at the history of science, it is tempting to imagine that black holes only appeared in the 20th century as products of Einstein's general relativity. In truth, the seeds of the idea stretch back much earlier, to a time when physics was still wearing the clothes of natural philosophy, when telescopes were crude and the universe itself seemed infinitely more modest than we now know it to be. In 1783, the English clergyman and scientist John Michell wrote a remarkable letter to the Royal Society. At a time when Newton's law of universal gravitation was the dominant framework, Michell considered a thought experiment. What if a star was so massive and its surface gravity so great that not even light could escape? He calculated, using Newtonian mechanics, that if a star's escape velocity exceeded the speed of light, which was already known thanks to old Romer's 1676 measurements, then the star would be effectively invisible. No light would reach us, and yet its gravitational presence could still be felt in the motions of nearby bodies. Michell called these hypothetical bodies dark stars. His reasoning was strikingly modern. He imagined entire populations of such objects scattered through space, hidden from view, detectable only through their effects. He even suggested that astronomers might infer their presence if binary stars appeared to orbit an unseen partner. In an era before photography, spectroscopy, or even reliable telescopes for faint stars, this was an astonishing leap. A few years later, in 1796, the French mathematician Pierre-Simon Laplace echoed the same idea in his Exposition du système du monde. He too argued that a sufficiently massive body would not allow light to escape, rendering it invisible. His discussion, however, was more of a passing curiosity, a speculative flourish in a book aimed at the educated public. By the early 19th century, these dark stars slipped into obscurity. The scientific world had little appetite for objects that could not be observed, and without a broader theoretical framework, the idea gathered dust. It would take over a century and the arrival of Einstein before the notion of light-trapping stars resurfaced with mathematical inevitability. In November 1915, Albert Einstein presented his general theory of relativity to the Prussian Academy of Sciences. It was a radical reshaping of gravity. Where Newton had described it as an invisible force acting at a distance, Einstein described it as the curvature of space-time itself. Massive objects told space-time how to bend, and space-time told objects how to move. Light, too, would follow these curves, bending its path near stars and planets. Within months of Einstein's publication, a German physicist named Karl Schwarzschild, serving on the front lines of World War I, found a solution to Einstein's daunting field equations. It described the space-time geometry around a perfectly spherical, non-rotating mass. Schwarzschild's result contained a curious feature. At a certain radius, later called the Schwarzschild radius, the equations suggested a boundary beyond which no signal could return. Inside this surface, escape velocity exceeded the speed of light. Schwarzschild's paper, published in 1916, marked the true birth of what we now call the event horizon. Though Einstein himself was uneasy with the idea, dismissing such singular solutions as mere mathematical oddities, the geometry was unavoidable. For any mass, there existed a critical radius where space and time seemed to collapse into paradox. For the Sun, this radius would be about 3 kilometers. For Earth, less than a centimeter. Compress either body into that size, and they would become black holes. Still, in the early decades of the 20th century, physicists regarded this Schwarzschild singularity as a curiosity. They assumed nature would find a way to avoid such extremes. Stars, it was thought, might explode or fragment long before reaching such compactness. Only with advances in astrophysics, particularly the understanding of stellar collapse in the 1930s, thanks to Subramanian Chandrasekhar's work on white dwarfs, did the spectre of black holes return with force. But the mathematics was clear. The event horizon was not just a strange artifact. It was a real boundary woven into the equations of relativity. And at the very center of the Schwarzschild solution lay something even more troubling: the singularity, a point where density became infinite, and the known laws of physics broke down entirely. Singularities are unsettling. They are places where mathematics signals its own failure, where infinities arise, and where predictive power ends. Physicists do not like them, yet they are stubbornly present in the equations. In the case of black holes, the singularity represents the ultimate gravitational collapse, all mass compressed into a zero-volume point. Whether such singularities truly exist in nature remains one of the great open questions of modern physics, but their presence in Einstein's framework was enough to ignite decades of debate. By the 1960s, that debate took a dramatic turn. Roy Kerr, a New Zealand mathematician, extended Schwarzschild's solution to the case of rotating bodies. In 1963, he published what became known as the Kerr metric, a solution describing the space-time around a rotating black hole. This was more than a mathematical curiosity. It was physically realistic. Almost no massive body in the universe is perfectly still. Stars spin. Galaxies spin. Collapse would almost always produce a rotating remnant. The Kerr solution introduced remarkable new features. Instead of a single horizon, rotating black holes have two: an outer event horizon and an inner Cauchy horizon. Between them lies a region called the ergosphere, where space-time itself is dragged along by the black hole's rotation. In this warped region, nothing can remain stationary relative to the distant universe. Even light is swept around, compelled to co-rotate. Yet paradoxically, energy can be extracted here, a process proposed by Roger Penrose in 1969, suggesting that particles entering the ergosphere could, under the right conditions, yield more energy than they carried in. It was the first hint that black holes might not only swallow energy, but release it. The richness of these solutions transformed black holes from mathematical oddities into plausible astrophysical objects. The discovery of quasars in the early 1960s, luminous, compact sources billions of light-years away, lent further support. Nothing known could power such brilliance except the accretion of matter into supermassive black holes. Suddenly, the theory had an anchor in observation. But let us step back for a moment and consider how remarkable this journey is. From Michel's musings in 1783 to Schwarzschild's wartime calculations in 1916 to Kerr's elegant equations in 1963, the path is one of persistence. Each stage deepened the paradox. Objects that by definition cannot be seen, yet whose existence is compelled by the mathematics of gravity. And each step drew us closer to the realization that the universe is stranger and darker than our imaginations alone would dare. To think of a black hole is to think of thresholds. The threshold of visibility, where light itself is trapped. The threshold of knowledge, where singularities defy comprehension. The threshold of possibility, where rotation twists spacetime into new shapes. And though these thresholds are theoretical, they set the stage for observation. For when the Event Horizon Telescope finally revealed the shadow of M87 star in 2019, it was not a surprise conjured from nothing. It was the culmination of centuries of thought, each equation a stepping stone, each paradox a challenge answered by new insight. Perhaps there is something poetic in the fact that the first glimpses of black holes came not from telescopes, but from the imagination of theorists. Michel, with his invisible stars, Schwarzschild scribbling equations under wartime skies, Kerr refining geometry with quiet elegance. These figures remind us that science is not only about what we can see, but about what we can reason. The shadows cast in mathematics often precede the shadows cast in the sky, and so by the mid-20th century, the stage was set. Black holes had evolved from curiosities into necessities. The universe, it seemed, demanded them. All that remained was to find a way to catch their shadows, to transform theory into image and mathematics into photograph. The word shadow usually conjures something familiar, a dark outline cast on the ground when an object blocks the light. Yet the shadow of a black hole is nothing like the silhouette of a tree at dusk or the figure of a person walking past a lamp. It is stranger, subtler, and more paradoxical. To understand it, we must turn to the way light itself bends in the presence of extreme gravity. In ordinary life, light seems stubbornly straight. Shine a flashlight through dust, and its beam travels in a rigid line. Look across a room, and the photons from the window to your eye seem to cut an unwavering path. But gravity, Einstein showed us, changes this rule. Space and time curve in the presence of mass, and light follows those curves. Around the Earth, the effect is too small to notice with the naked eye, but around a star, it becomes measurable. During the 1919 solar eclipse, Arthur Eddington's team famously confirmed Einstein's prediction by observing starlight bent as it passed near the Sun's limb. The stars appeared shifted, displaced by the Sun's gravitational lens. Now imagine pushing this effect to the extreme. Near a black hole, gravity bends space-time so violently that light rays can be caught, trapped, even forced into orbit. There exists a particular radius, known as the photon sphere, where light does not escape outward or fall inward immediately, but loops around the black hole in precarious, unstable circles. For a non-rotating Schwarzschild black hole, this radius lies at 1.5 times the Schwarzschild radius. Any photon straying here traces a doomed orbit, a single nudge, and it will either spiral outward to infinity or plunge irreversibly through the horizon. This photon sphere is not a solid surface. It is not a boundary you could touch. It is more like a ghostly shell, a gravitational mirage suspended in space, and yet it plays a central role in shaping what we see. Photons grazing just outside the photon sphere bend dramatically around the black hole before reaching us, creating the warped image of background stars and glowing gas. Photons that venture just inside are lost forever. The dividing line between these two fates is what outlines the shadow. This is why the shadow of a black hole is not the event horizon itself. The horizon lies deeper in, invisible by definition. What we actually see is the capture cross-section of light, the footprint left by all the photons that failed to escape. The result is a dark disk, larger than the horizon, surrounded by distorted light. For a Schwarzschild black hole, this shadow is about 2.6 times larger in radius than the event horizon. In other words, the black hole looks bigger than it really is, its darkness magnified by the lensing of spacetime. The shape of this shadow carries the fingerprint of gravity. For a perfectly spherical black hole, it is nearly circular. For a rotating Kerr black hole, it becomes subtly distorted, flattened on one side by frame dragging. The brightness of the surrounding ring is not uniform either. Relativistic beaming, the same effect that makes a car's headlights seem brighter when it rushes toward you, enhances the glow on one side, where plasma is moving toward us at near light speeds. Thus, the The famous donut image of M87 star is not just a circle of fire. It is a map of space-time, motion, and gravity etched in light. This understanding, however, was not born in the age of supercomputers. Its roots reach back to the late 1970s, when a French astrophysicist named Jean-Pierre Luminet produced what is now recognized as the first realistic simulation of a black hole's appearance. Luminet's 1979 paper, published in Astronomy and Astrophysics, carried an image that, even decades later, looks hauntingly familiar. Using nothing more than a computer program and stacks of punch cards, he calculated how light rays would bend around a black hole surrounded by an accretion disk. The result was a warped, luminous ring, brighter on one side, with the far side of the disk bent upward by gravity. It was the first visualization of what would one day become a real photograph. The image was not generated casually. Luminet spent long nights programming on the computers available at the Paris Meudon Observatory, running calculations of photon trajectories under general relativity. The machines could not render graphics as we know them today, so Luminet painstakingly translated numbers into images by hand, using an ink plotter to shade pixels. The final result was grainy and monochrome, but it revealed something astonishing. The universe, through relativity, produces a kind of natural surrealism. The black hole did not simply swallow light, it bent and magnified, distorted and twisted, turning a flat disk into an otherworldly halo. In that sense, Luminet's work was an act of imagination grounded in physics. He had never seen such an object. No one had. Yet the equations demanded it, and he gave the equations a face. For 40 years, that face would remain theoretical, tucked into textbooks and lectures. But when the Event Horizon Telescope unveiled M87 star in 2019, the resemblance was uncanny. What Luminet had traced in ink decades earlier became a photograph on screens around the globe. It is worth pausing here to appreciate the audacity of that moment in 1979. Computers were primitive, data storage tiny, and yet a single scientist, armed with equations and patience, sketched the first shadow of a black hole. It is a reminder that seeing is not always the beginning of knowledge. Sometimes, knowledge itself prepares the way for seeing. The phenomenon of gravitational lensing, which underpins this shadow, deserves a closer look. When light passes near a massive object, its path curves. On cosmic scales, galaxies and clusters of galaxies act as colossal lenses, bending the light of background galaxies into arcs and rings. Astronomers now use this effect routinely to map dark matter and probe the distant universe. But around a black hole, the lensing is extreme. Light can loop around once, twice, many times, producing a series of faint, concentric rings known as photon rings. Each ring represents photons that orbited the hole an additional time before escaping. In principle, an infinite number of these rings exist, each smaller and fainter than the last, stacking endlessly toward the shadow. The Event Horizon Telescope cannot resolve these delicate photon rings, at least not yet, but future instruments may. To capture even a glimpse of these nested circles would be to see space-time's handwriting with exquisite clarity. It would also provide one of the most precise tests of general relativity possible, for the shape and size of the shadow and the spacing of the rings are dictated by Einstein's equations. Deviations could hint at new physics, perhaps even clues to quantum gravity. But beyond the technical details, there is something profoundly human about calling this void a shadow. The word anchors an alien phenomenon in everyday experience. We know shadows. They accompany us in sunlight, stretch across walls, flicker in candlelight. To apply the same word to a black hole is to remind ourselves that even the strangest corners of the cosmos can be understood through familiar metaphors. A black hole does not cast its shadow on a wall, but on the universe itself. And what a peculiar shadow it is. Unlike ordinary shadows, which vanish when the light source moves, this one is eternal. It is cast not by blocking light, but by consuming it. It does not depend on the angle of illumination, for the black hole is illuminated from every direction by background stars, by infalling gas, by radiation from the cosmos. The shadow is not the absence of a beam, but the universal absence of escape. When we look at the shadow of a black hole, we are not seeing matter, but geometry. We are witnessing the architecture of space-time itself. The circle we see is drawn not by hand, but by the curvature of the universe around mass pushed to its extreme. In that sense, the black hole shadow is a portrait not of the object, but of the theory, general relativity traced in firelight. And yet, even this profound realization carries a whisper of humility. For all our telescopes and simulations, we are still staring at an outline. The interior remains hidden, unknowable. The singularity, if it exists, lies forever beyond reach. The shadow is a boundary, a cosmic censorship, reminding us of the limits of knowledge. It is both revelation and concealment. Perhaps that is why the image of M87 struck such a chord. It was not sharp or dazzling. It was a blurry ring, orange against black. But in that blur lay the weight of a century of theory, the echo of Luminet's hand-drawn plot, the bending of photons that had traveled 55 million years to reach us. To gaze at it was to see the universe refusing to let light go, and in that refusal, to reveal a shadow more eloquent than any brightness. For most of the 20th century, black holes were creatures of mathematics. Equations could describe them, predict their effects, and even estimate their shadows, but no telescope could hope to resolve them. They were too small in the sky, too distant, and their most obvious feature, their invisibility, offered no easy signature. And yet, human imagination is restless. If we cannot see directly, we simulate. If reality hides, we conjure it in calculation. That is what a handful of physicists and astrophysicists began doing in the second half of the 20th century, sketching what a black hole would look like, if only we could build the eyes large enough to see. These early simulations, primitive by today's standards, were acts of both rigor and artistry. They used ray tracing, a technique borrowed from optics and computer graphics, to follow the paths of light in warped space-time, mapping how an observer would perceive a black hole's environment. Ray tracing, at its simplest, is the idea of following photons backward. Instead of sending light outward from a source and waiting for it to bounce back, one imagines rays traveling from the observer's eye, or the camera, into the scene. Each ray is traced through the environment to determine what object it encounters, what color it carries, how it bends or reflects. In the context of black holes, this technique becomes more profound. Rays must obey Einstein's geodesics, curving in response to space-time itself. They can loop around the black hole, scatter, or fall inward. The question for the simulator is, where does each ray end up? Does it emerge from the glowing accretion disk, the distant background stars, or nowhere at all, swallowed into the horizon? Jean-Pierre Luminet's 1979 work was the first striking example of this approach. Using punch cards and numerical integration, he painstakingly traced light rays through the Schwarzschild geometry, surrounding the black hole with a thin accretion disk. The result, as we've already seen, was an image of startling strangeness. The near side of the disk appearing brighter due to Doppler beaming, the far side lifted into view by gravitational lensing, the central void marked by darkness. It was the first attempt to show the human eye what the mathematics implied. But Luminet was not alone. Throughout the 1980s and 1990s, advances in computing allowed more researchers to try their hand at visualizing black holes. Each decade added refinement, better resolution, more realistic accretion models, color renderings instead of monochrome. By the 1990s, simulations by scientists like Jean-Alain Marc in France and Andrew Hamilton in the United States produced fly-throughs of black hole environments, depicting what it might look like to fall toward the horizon. The distortions they revealed were surreal. A star field behind the black hole would appear doubled, light rays bent into arcs that wrapped around the hole. The accretion disk would no longer resemble a simple flat structure. Instead, it would appear as a glowing halo encircling the void, with its far side mirrored and inverted. The closer you moved, the more extreme the lensing became, until the universe itself seemed folded around the event horizon like a hall of mirrors. These were not just parlor tricks. The distortions encoded physics. They revealed how light behaves near the photon sphere, how time dilation stretches events as matter spirals inward, how relativistic beaming brightens one side of the disk while dimming the other. They showed that black holes are not only dark, but also luminous in their periphery, sculptors of light as much as swallowers of it. Why were these simulations scientifically useful? In part, because they gave theorists and observers a target. Before a telescope gathers data, one must know what to look for, what patterns might emerge from the noise. The human brain is good at recognizing shapes when primed to expect them. By producing images, even simulated ones, astrophysicists could train themselves and their colleagues to recognize the distinctive signature of a black hole shadow. They were also useful for testing relativity. The shape of the shadow, the distortion of the disk, the position of photon rings, all of these could be derived precisely from Einstein's equations. Simulations allowed scientists to compare in advance what different theories of gravity would predict. Deviations from circularity, shifts in brightness, subtle asymmetries, all could serve as diagnostic tools. When the Event Horizon Telescope finally produced real data, these earlier models were the yardsticks against which the image was measured. It is worth remembering that in the 1970s and 80s, no one knew for sure whether black holes truly existed. They were strong theoretical candidates, invoked to explain X-ray binaries, quasars, and galactic nuclei, but direct confirmation was lacking. To draw them, to simulate their appearance, was to stake a claim that these exotic solutions of Einstein's equations corresponded to actual astrophysical objects. The act of visualization was itself a vote of confidence in the reality of black holes. There is another reason these simulations mattered. They inspired. When students and researchers saw Luminet's plots or Marc's animations, they felt they were peeking into the forbidden. Science is, at its best, a blend of rigor and imagination. Numbers alone can feel abstract. Images, even simulated ones, invite wonder. They let us say, this is what the abyss might look like. In doing so, they kept alive the dream of one day seeing for real. As computers improved, the fidelity of these simulations grew. By the early 2000s, physicists could produce high-resolution renderings that incorporated not just light bending, but also magnetohydrodynamic models of accretion flows. These images showed turbulent plasma, jets launched by magnetic fields, and chaotic brightness patterns near the horizon. They suggested that black hole shadows would not be smooth rings, but dynamic, flickering halos, a crucial insight for interpreting future observations. One striking example came from Andrew Hamilton's team at the University of Colorado, which produced public Journey into a Black Hole animations. These visualizations, freely available online, allowed anyone to imagine falling past the photon sphere, watching the universe wrap around itself as the horizon loomed. Though no human will ever survive such a trip, the simulation brought the experience into our living rooms. It was both pedagogy and poetry. By the time the Event Horizon Telescope collaboration formed in the late 2000s, these simulations had accumulated into a library of expectations. They helped scientists design observing strategies, choose wavelengths, and anticipate the scale of features to look for. When the real image of M87 star emerged in 2019, its blurry ring of light was not a surprise conjured from the void. It was the confirmation of decades of simulated anticipation. And yet, one might argue that these early images were more than just preparation. They were acts of faith. Faith that mathematics corresponds to reality. Faith that unseen objects can be made visible, at least in theory. Faith that one day technology would catch up, and the line between simulation and photograph would blur. That faith was vindicated spectacularly when the first black hole shadow appeared on screens around the world. Still, even today, simulations remain essential. The Event Horizon Telescope produces data that must be reconstructed through complex algorithms. To verify those reconstructions, scientists compare them against simulated black holes generated under various physical assumptions. Do the features match? Are the asymmetries consistent with relativistic beaming? Does the ring size correspond to the predicted photon sphere? Without simulations, the image could not be interpreted. In that sense, every photograph of a black hole is still half drawn by theory. There is also a deeper philosophical lesson in these precursors. Long before we saw black holes, we imagined them. And our imagination was disciplined by mathematics, guided by equations that dictated how light bends and how matter glows. This interplay of imagination and rigor is what defines much of modern science. To draw what you cannot see but what you can calculate is to let theory paint reality. And when reality later confirms the painting, the satisfaction is profound. In the end, these early simulations remind us of a truth that runs throughout science. Images are not just outputs, they are instruments of thought. They allow us to test, to anticipate, to inspire, and to bridge the gap between numbers and experience. When Jean-Pierre Luminet fed his punch cards into the computer in 1979, he could not have known that 4 decades later, a global collaboration would present the world with a nearly identical image. Yet the connection is unmistakable. The ink lines of his plotter were the prelude to the fiery ring of M87 star. The imaginative precursors, then, were never idle sketches. They were rehearsal. They trained our eyes to see shadows where none had been seen before, and in doing so, prepared humanity for the moment when the darkness at the heart of a galaxy would finally stare back. For all their fame, black holes remain the most reluctant of cosmic actors. Stars shine, galaxies glitter, nebulae glow with soft light. But a black hole? By definition, it offers nothing. It is a stage without a spotlight, a performer who refuses to step forward, leaving only the scenery around it to hint at its presence. If you wanted to design the least photogenic object in the universe, you could hardly do better. The problem begins with the event horizon. Unlike the surface of a planet or the face of a star, the horizon is not made of matter. It is a boundary in space-time, a one-way membrane. Cross it, and there is no return. Not for matter, not for radiation, not even for light. The darkness is absolute because nothing escapes to tell the tale. A camera pointed at the horizon would record no photons, no reflections, no signal at all. It is the perfect absorber, a cosmic black velvet curtain that swallows every spotlight trained upon it. This is why the phrase photographing a black hole is, strictly speaking, misleading. We cannot photograph the black hole itself. What we capture is its influence on the things around it, the distorted glow of infalling matter, the bending of background light, the outlines sketched by absence. The hole itself is not the subject of the photograph, but the blank space at its center. It is a picture drawn in negative, and so we turn our gaze to what surrounds it. Around many black holes lies an accretion disk, a swirling whirlpool of gas and dust spiraling inward. As matter falls, it heats through friction and compression, reaching millions of degrees. Such plasma radiates ferociously, emitting in radio, X-ray, and gamma-ray wavelengths. Some of this light, bent by the black hole's gravity, forms the bright ring we see in images like M87 star, but disks are not the only sources of brightness. Some black holes, particularly the supermassive ones at the centers of galaxies, launch jets, colossal streams of plasma accelerated to near light speed, stretching across thousands of light-years. These jets shine brightly in radio and X-ray, sometimes visible across intergalactic space. In fact, long before black holes were photographed, astronomers suspected their presence precisely because of these jets. Something in the heart of galaxies was generating power beyond what any star cluster could manage, and the prime suspect was a supermassive black hole feeding on matter and spitting energy outward. There are also background sources. A black hole is rarely isolated. Behind it lie the stars of its host galaxy, the diffuse glow of gas, and the faint light of the universe at large. All of these photons may skim close to the horizon, their paths bent and twisted into arcs, rings, and mirages. In effect, the black hole acts as a lens, but a lens whose central region is missing, swallowed into darkness. This is the irony. Black holes are invisible, and yet their invisibility can be highlighted by light. The glowing accretion disk, the beamed jets, the distorted backdrop, these are the brushes with which nature paints the portrait. Without them, the whole would vanish completely, unmarked and undetectable. With them, its outline appears. It is as though the universe conspires to frame the unseeable with luminous scaffolding, a halo of brilliance around a void. But even with this luminous assistance, the challenge of seeing a black hole remains daunting. The issue is scale. Consider Sagittarius A star, the supermassive black hole at the center of our Milky Way. Its mass is about 4 million suns, with a Schwarzschild radius of around 12 million kilometers. On human terms, this is immense, large enough to encompass the orbit of Mercury. And yet, because it sits 26,000 light-years away, its apparent size in our sky is absurdly small. From Earth, the shadow of Sagittarius A star subtends an angle of about 50 microarc-seconds. That is like trying to resolve a grapefruit on the surface of the moon, or a single grain of rice in New York while standing in Paris. M87 star, the black hole imaged in 2019, is even larger in physical scale, about 6.5 billion solar masses. Its event horizon could swallow our entire solar system, yet it lies 55 million light-years away. From Earth, its angular size is comparable to Sagittarius A star, again on the order of tens of microarc-seconds. Telescopes, like cameras, are limited by diffraction. The resolving power depends on the wavelength of light and the diameter of the aperture. To see something as small as a black hole's shadow, we would need a telescope the size of Earth itself. Since no single dish could be that large, astronomers turn to a trick called very long baseline interferometry, combining signals from widely separated telescopes into a synthetic aperture. But even with this innovation, the angular scale pushes the very edge of what is possible. This tiny size creates another problem: interstellar scattering. On the way to Earth, light from Sagittarius A star must pass through turbulent clouds of plasma in the galaxy. These act like frosted glass, blurring the image. The effect is similar to looking at a distant street lamp through heat shimmer. For decades, astronomers knew that scattering would make Sagittarius A star extremely difficult to image, even if its size was technically resolvable. In fact, one reason M87 star was chosen for the first attempt was that its light suffers far less scattering on its journey to Earth. The smallness of the target also magnifies noise. Every fluctuation in the atmosphere above each telescope, every tiny calibration error, every jitter in the timing of atomic clocks, All of these ripple into the final image. When you are trying to capture something no larger than a grapefruit on the moon, even the smallest distortion matters. It is like asking a camera to take a long exposure shot of a firefly in a hurricane. The camera shyness of black holes, then, is not just metaphor. It is the practical outcome of physics. They emit nothing of their own. They cloak themselves in scale so small that our instruments struggle to grasp them. They hide behind turbulence, blur, and noise. And even when revealed, they offer only a ring around a void, a portrait that seems incomplete, as if the subject has turned its face away. And yet, this very reluctance is what makes the achievement of photographing them so profound. To wrest an image from an object designed by nature to remain unseen is to push human ingenuity to its limits. It demands not only giant telescopes, but global collaboration, synchronization to billionths of a second, petabytes of data, and years of patient analysis. The shadow is not given freely. It must be coaxed, reconstructed, teased from the silence. In a sense, this makes the photograph of a black hole a mirror of our own determination. We live in a universe that does not hand us its secrets easily. The most important truths about origins, about fate, about the limits of space and time are hidden behind veils. And still we reach for them, inventing new methods, imagining what cannot be seen, building instruments the size of continents. The black hole's shyness is part of its allure. The more it refuses to be seen, the more determined we are to see it. It is perhaps no accident that in mythology and folklore the most powerful beings are often invisible. The gods of old thundered from behind clouds, spirits lurked unseen in forests, monsters dwelled in shadows. To make the invisible visible has always been one of humanity's deepest desires. The black hole is the modern echo of this ancient theme, a cosmic shadow that hides from our gaze until we invent new eyes to reveal it. So, why are black holes camera shy? Because they are defined by their silence, their refusal, their vanishing act. But like the shyest of subjects, they give themselves away in subtle gestures. The swirl of plasma, the bend of light, the tiny circle in the sky. And with enough patience, enough ingenuity, we can catch them in the act and bring their shadows into focus. The idea of photographing a black hole once sounded like fantasy. Astronomers had accepted for decades that such objects might exist, their presence betrayed in X-ray binaries, their power hinted at in quasars. But to actually see the shadow, to produce an image sharp enough to reveal the silhouette of the event horizon, seemed impossible. And yet, impossibility has always been the cradle of invention. The problem was scale. To resolve the tiny angular size of Sagittarius A star or M87 star, one would need a telescope with a dish as wide as the Earth itself. Building such a structure was, of course, absurd. No engineering could sustain it. But engineers and astronomers had already begun experimenting with a clever substitute, very long baseline interferometry, or VLBI. The principle of interferometry is simple to state, though devilishly complex to execute. If two telescopes look at the same source, separated by some distance, they both collect incoming radio waves. These signals are not identical because the wavefront reaches each dish at a slightly different time. By carefully comparing the two recordings, aligning them down to fractions of a wavelength, astronomers can measure the interference pattern between them. The greater the separation, or baseline, the finer the details that can be resolved. VLBI pushes this principle to its extreme. Instead of placing telescopes next to one another, it scatters them across the Earth. Dishes in Hawaii, Spain, Chile, Antarctica, and beyond all turn to the same cosmic target. Their signals are recorded on high-speed drives, time-stamped by atomic clocks, and later brought together for correlation. In effect, the Earth itself becomes one giant dish, its diameter defined by the maximum separation between telescopes. This technique was pioneered in the 1960s, originally as a Cold War tool. By measuring the positions of quasars with extraordinary precision, VLBI helped geodesists track continental drift and the wobble of Earth's axis, but astronomers quickly realized its potential for imaging. By the 1970s, VLBI arrays were mapping the jets of radio galaxies, revealing structures invisible to single-dish telescopes. It was only a matter of time before someone asked, could this be pushed further? Could VLBI, scaled up to a global network, resolve the infinitesimal shadows of black holes? The idea simmered for decades, nurtured by advances in technology. VLBI required not only multiple telescopes, but the ability to synchronize them with exquisite precision. The timing had to be accurate to billionths of a second, or the interference pattern would dissolve into noise. This demanded atomic clocks, hydrogen mesas, humming away in observatory basements, their steady oscillations marking time with unmatched fidelity. Then there was the problem of data. Each telescope recorded torrents of information, terabytes per night. In the early years, such volumes were unmanageable. Drives were too small, networks too slow. But as storage technology leapt forward, the dream of stitching together global baselines became realistic. Instead of trying to transmit data through the internet, astronomers adopted a more old-fashioned solution, shipping the drives by airplane to central processing facilities, where they could be correlated on supercomputers. By the early 2000s, a small group of scientists began to seriously propose the construction of an Event Horizon Telescope, a planet-spanning array designed with one purpose: to image the shadow of a black hole. The name was aspirational, almost audacious. For a long time, many in the community doubted it could work. The sources were too small, the data too noisy, the logistics too daunting. But persistence, as always, turned doubt into design. One of the key questions was, at what wavelength should this Earth-sized telescope observe? Too long, and the resolution would be too coarse. Too short, and Earth's atmosphere would absorb or scatter the signals. The sweet spot turned out to be around 1.3 millimeters, or 230 gigahertz. At this wavelength, the diffraction limit of an Earth-sized array is roughly 20 microarc seconds, just enough to resolve the expected shadow of Sagittarius A star and M87 star. Shorter wavelengths, like 0.8 millimeters, could, in principle, offer even sharper resolution, but they suffer from severe atmospheric absorption, especially water vapor. Longer wavelengths, like 3 millimeters, pass more easily through the atmosphere, but their resolution blurs the shadow. There was another reason 1.3 millimeters was chosen: scattering. Light from Sagittarius A star, traveling through the turbulent plasma of the Milky Way, is smeared out at long wavelengths, like an image seen through frosted glass. Only at millimeter wavelengths does the scattering thin enough for the true shadow to emerge. At 1.3 millimeters, the blur is comparable to the size of the shadow itself, making it possible, though just barely, to separate signal from distortion. The decision was a compromise: short enough for resolution, long enough for atmospheric transparency, and just right to pierce the galactic fog. It was the wavelength of possibility, a narrow window through which the shadow of a black hole could be glimpsed. With the wavelength chosen, the next task was global architecture. No single observatory could span the Earth. Instead, existing radio telescopes were recruited into the array. Hawaii's sub-millimeter array, perched atop Mauna Kea, offered a Pacific anchor. The Atacama Large Millimeter/Sub-Millimeter Array, ALMA in Chile, with its 66 antennas, provided unmatched sensitivity in the southern hemisphere. The IRAM 30-meter telescope in Spain covered Europe. the South Pole Telescope gave baselines stretching across the globe's longest chord. Gradually, more were added in Mexico, Arizona, Greenland. Each new site filled a gap, sharpening the synthetic aperture. But these telescopes were not originally designed to work together. They differed in hardware, in calibration, in local conditions. Integrating them required enormous effort: new receivers, new recording systems, new methods of synchronization. The EHT was not so much a single instrument as a symphony of disparate voices, all forced into harmony. The coordination extended beyond hardware. Observations had to be simultaneous across all sites, often over multiple nights, with weather cooperating everywhere at once. A cloud over Hawaii, a storm in Spain, a burst of humidity in Chile, any of these could doom the attempt. It was like trying to stage a global performance where every musician, scattered across continents, must play the same note at the same time, perfectly in tune. And yet, despite the fragility of the setup, the network grew stronger. Each year, more baselines were added, sensitivity improved, and algorithms refined. The concept of an event horizon telescope shifted from dream to reality. By the late 2010s, the stage was set for its first grand campaign. What makes the EHT extraordinary is not only its engineering, but its philosophy. Most telescopes look outward at many targets, surveying the sky. The EHT, by contrast, is almost monastic in focus. It is built for shadows. Its entire architecture, from atomic clocks to cryogenic receivers, is devoted to glimpsing the tiny voids at the hearts of galaxies. In that sense, it is less like a general-purpose observatory and more like a precision instrument, a scalpel aimed at space-time itself. This specialization underscores the ambition of the project: to build a telescope the size of Earth, synchronize across continents, record oceans of data, and all for the sake of imaging a ring of fire around a darkness. It is one of the most audacious scientific acts of the 21st century. And yet, it is precisely in such audacity that discovery flourishes. Because the EHT is more than just an experiment. It is a demonstration of possibility, that by joining instruments across the globe, humanity can transcend the limits of geography. It is also a demonstration of humility, that to glimpse a shadow, we must cooperate on a planetary scale, and, in a way, it is a mirror. The Earth itself becomes the telescope, as if the planet were straining to peer into the abyss. Even now, the EHT is not static. New telescopes are being added, new wavelengths explored, new algorithms developed. At shorter millimeter bands, sharper images await. Space-based extensions, perhaps someday on the Moon, could expand the baselines beyond Earth itself, bringing shadows into even finer focus. But the concept, the heart of the matter, remains the same: to build a telescope as large as the question demands, to scale our instruments until they match the scale of the mystery, to turn the entire Earth into an eye, gazing across millions of light-years at the faint outline of darkness. The birth of the Event Horizon Telescope was not a single moment, but a slow awakening, an idea whispered in the halls of radio astronomy, nurtured by technology, and finally brought into being by the stubborn insistence that even shadows can be photographed. And perhaps that is its deepest lesson. The universe does not yield its secrets easily. But when we ask with patience, when we build with daring, when we join hands across continents, even the most camera-shy of cosmic actors will step into the light, or, more fittingly, into the darkness framed by light. In April of 2017, years of planning, debate, and engineering coalesced into a single experiment. For 5 nights, telescopes across the globe pointed their dishes toward two of the most elusive objects in the universe: Sagittarius, a star, the supermassive black hole at the center of our own galaxy, and M87 star, the gargantuan black hole in the core of a giant elliptical galaxy 55 million light-years away. This campaign was the culmination of the Event Horizon Telescope's long gestation. For decades, scientists had rehearsed in theory and simulation. Now it was time to try for real, to turn the Earth into a single instrument, synchronizing observatories scattered across continents and hemispheres, each playing its role in a planetary symphony. The logistics alone were staggering. 8 observatories were involved in the 2017 array, chosen for their location, altitude, and equipment. On Mauna Kea in Hawaii, the submillimeter array and the James Clerk Maxwell telescope provided a vital Pacific anchor. In Chile's Atacama Desert, the Atacama Large Millimeter/Submillimeter Array, or ALMA, contributed its vast sensitivity, the power of dozens of antennas acting as one. In Spain, the IRAM 30-meter telescope tuned its giant dish to the same frequency, bridging Europe to the Americas. The South Pole telescope gave the array its most extreme baseline, stretching the virtual aperture nearly across the planet's diameter. Additional partners included the Large Millimeter Telescope in Mexico, the Submillimeter Telescope in Arizona, and the Greenland Telescope. Together, they stitched the globe into an eye with a resolution fine enough to glimpse a black hole's shadow. Each site had to be precisely synchronized. Signals were recorded not in the form of pretty images, but as torrents of raw voltage data, the oscillations of radio waves captured by each dish. To align these signals later, atomic clocks at every observatory ticked in unison, their stability measured in billionths of a second. A hydrogen maser, humming in a quiet room beside each telescope, marked the passage of time with such fidelity that over 1 million years it would drift by less than a second. Without such clocks, the signals from different sites would lose coherence, their interference patterns dissolving into meaningless noise. And then there was the sky itself. Observing at 1.3 millimeters is treacherous. The atmosphere absorbs and scatters radiation at this wavelength, especially water vapor. That is why the telescopes had been chosen for dry, high-altitude locations, deserts, mountain tops, even the frozen Antarctic plateau. Yet even here, weather could interfere. A passing cloud over Hawaii, a gust of humidity in Chile, turbulence in Spain, any of these could corrupt the data. For the campaign to succeed, conditions had to align across continents at once, a global roll of the dice. On those April nights, the world held its breath. The telescopes tracked their targets, their giant dishes turning in sync to follow the faint glow of plasma swirling around horizons. For hours at a time, they collected signals, writing them onto banks of high-speed drives. The data rates were enormous, gigabytes per second, too vast to be transmitted over networks. Instead, petabytes of storage were physically shipped by airplane to 2 central correlating facilities, one at MIT's Haystack Observatory in Massachusetts, the other at the Max Planck Institute for Radio Astronomy in Bonn, Germany. It was a return to an older era of science, when results traveled in crates rather than through fiber optics. What those drives contained was not an image, at least not in the ordinary sense. No photograph could be pulled from them, no glowing ring visible at first glance. Instead, they held fragments of waveforms, radio signals from each telescope, shifted slightly in time depending on distance and geometry. The task ahead was to combine them, aligning their phases, correlating them across baselines. In effect, scientists had captured pieces of a cosmic puzzle. Only by overlaying those pieces with exquisite care could the picture emerge. The nature of the data was humbling. Imagine trying to take a photograph of a distant mountain range by asking different friends, scattered across the countryside, to close their eyes and record when the echoes of a single gunshot reached them. Later, by comparing all the timings, you could reconstruct not the sound itself, but the layout of the landscape that reflected it. That is what VLBI does, but with waves billions of times faster than sound, captured across the Earth, arriving from light years away. The image exists only in the interference pattern, the correlations of phase and amplitude. To make sense of it requires mathematics as much as optics. Noise was the ever-present enemy. Every telescope has imperfections. Receivers hum, electronics add jitter. The atmosphere wobbles unpredictably. To tease out the faint signal of a black hole shadow, scientists had to calibrate meticulously. They corrected for atmospheric delays, for variations in antenna sensitivity, for differences in polarization. They tested the stability of each baseline, discarding corrupted segments, reweighting others. Entire teams devoted themselves to error analysis, ensuring that the emerging picture was not an artifact of bias or assumption. And then there was the problem of variability. Sagittarius A star flickers rapidly, its plasma changing on minute timescales. The Earth-sized telescope, meanwhile, takes hours to fill its Fourier plane. The mathematical space where visibilities are recorded. The result is a mismatch. The object changes while you try to image it, like a portrait subject who won't sit still. This is why, for the first campaign, much of the focus fell on M87 star. Though far more distant, its massive scale means it evolves slowly, on timescales of days to weeks. Its image, unlike Sagittarius A star, could be treated as static during observation. The nights were long, the stakes high. At each observatory, teams huddled in control rooms, watching as drives filled and antennas tracked. Some had traveled thousands of miles to sit in those rooms, waiting for clear skies and stable equipment. In Hawaii, snow sometimes dusted the domes on Mauna Kea. In Chile, the Atacama Plateau baked under the thin desert air. At the South Pole, winter was just beginning, the sun dipping below the horizon for months to come. Everywhere, the hum of hydrogen masses marked the steady beat of time, keeping the whole planet in rhythm. By the end of the campaign, hundreds of terabytes of raw data had been collected, the largest VLBI experiment ever attempted. Yet no one knew, in those first days, whether the shadow had truly been captured. That answer would come only after months of analysis, correlation, and independent verification. But already, there was a quiet sense of awe. For 5 nights in April, humanity had turned Earth itself into a telescope. From pole to desert, mountain to plateau, dishes had moved in unison, their signals joined across oceans and continents. The project was audacious not only in science, but in spirit. No single nation, no solitary observatory could have done it. The shadow could be glimpsed only by acting together, by weaving the planet into a single eye. It is easy now to focus on the photograph that followed. The glowing ring unveiled in 2019, splashed across headlines, etched into collective memory. But before that image, there was this act of faith, scientists pointing their instruments at the void, gathering invisible signals, trusting that mathematics and patience would reveal what no one had ever seen. It was, in its way, a moment of collective stillness. Humanity stared into darkness and waited for the echo. The raw signals, once recorded, bore the subtle fingerprints of space-time. A photon leaving plasma near the horizon of M87 traveled 55 million years before striking a dish in Chile. Another photon, almost identical, reached Hawaii a fraction of a second later. Their arrival times differed by microseconds, their phases shifted by fractions of a wavelength. Yet in those differences lay the geometry of the black hole shadow. To combine them was to unlock a message carried across cosmic time. This is the nature of VLBI data. It is not an image, but a possibility. It is a set of correlations that hint at structure, waiting for reconstruction. In the 2017 campaign, that possibility became reality. But in those nights of April, it was still fragile. A dream written in voltages, spinning on hard drives, sealed in crates bound for Massachusetts and Bonn. One could argue that those drives, flown across oceans in ordinary airplanes, carried the most precious cargo in modern astronomy, the first raw glimpses of a black hole's shadow. They did not look like much, rows of metal and plastic packed in foam. Yet within them were waveforms older than humanity itself, radio whispers from the edge of a horizon, collected by instruments scattered across Earth and brought together by human determination. What makes this story so compelling is not only the science, but the symbolism. For 5 nights, our species synchronized across the globe, building an eye the size of a planet, straining to see into the abyss. The act itself was extraordinary, regardless of outcome. To attempt to photograph a shadow, to align clocks so perfectly that signals billions of years old could interfere constructively, is to declare that curiosity has no horizon. The 2017 campaign marked the transition from preparation to discovery. After decades of theory, years of planning, and countless simulations, the universe had been asked a direct question: will you show us your shadow? The answer would take months to decode, but already the data were on their way, traveling not at the speed of light, but at the speed of cargo planes and customs forms. And when those crates arrived, they carried not only petabytes of information, but the weight of centuries of imagination. The data collected in April 2017 were silent at first. Packed in crates, flown across oceans, carried into labs in Massachusetts and Germany, they sat like locked treasure chests. Each drive was filled with radio wave recordings from telescopes scattered across Earth, Hawaii, Chile, Spain, the South Pole, and beyond. But on their own, each fragment meant little. A single dish could not resolve the black hole shadow. It could only collect a blurry, noisy signal. The image would come only when the fragments were joined together, when the puzzle was assembled. The first step in this assembly was correlation. In VLBI, correlation is the act of combining signals from different telescopes, aligning them in time with exquisite precision. The trick is that each telescope records a waveform, the voltage fluctuations induced by incoming radio waves. These fluctuations appear chaotic, nothing more than noise. But buried in the chaos are patterns, faint, repeating structures that reveal the interference of signals across baselines. By comparing pairs of telescopes, scientists can measure how similar their waveforms are, offset in time by the geometry of Earth and the location of the source. At MIT's Haystack Observatory and at the Max Planck Institute for Radio Astronomy in Bonn, supercomputers known as correlators took on this monumental task. The correlators were specialized machines, designed to sift through petabytes of data, aligning each signal with nanosecond accuracy. Atomic clocks at each site had stamped every packet of data, ensuring that, no matter the distance, the signals could be synchronized later. The process was slow, careful, and computationally heavy, but it transformed raw noise into something more: visibilities. Visibilities are not images. They are measurements in Fourier space, the mathematical domain where an image is represented not as pixels, but as patterns of frequency and phase. Each baseline between 2 telescopes samples one point in this Fourier plane. The longer the baseline, the finer the detail it resolves. But no telescope array, not even one spanning the Earth, can fill this plane completely. There are gaps, holes, missing information. The art of imaging lies in using what is sampled to reconstruct what is missing. Here, the Earth itself plays a role. As the planet rotates, the relative positions of the telescopes change. A baseline between Hawaii and Spain, for instance, sweeps across different orientations as hours pass. This motion fills in more of the Fourier plane, providing additional samples. It is as if Earth were painting the invisible structure of the black hole shadow by turning slowly beneath it. Without Earth's rotation, the array would capture only a sparse skeleton of information. With it, the skeleton gains flesh. Once the visibilities were assembled, the task shifted to imaging. But imaging in VLBI is not straightforward. Unlike a digital camera, which converts photons directly into pixels, VLBI reconstructs images from correlations, a process more like solving a jigsaw puzzle with missing pieces. Multiple algorithms exist, each with strengths and weaknesses. Some, like CLEAN, are long-standing staples of radio astronomy, peeling away point sources and reconstructing extended structures. Others, like regularized maximum likelihood methods, impose constraints on smoothness, circularity, or brightness to guide the reconstruction. The Event Horizon Telescope collaboration took no chances. They established multiple independent imaging pipelines, each run by separate teams working in isolation. These teams did not communicate their results to one another during the initial stages. The idea was to avoid bias, to ensure that the final image was not the product of groupthink or expectation. If all the pipelines working independently produced the same structure, confidence in the result would be far stronger. Weeks turned into months as these teams labored. They fed the visibilities into their algorithms, adjusting parameters, testing assumptions. Synthetic data sets were created, mimicking the expected signal of a black hole shadow, to test whether the pipelines could recover known structures. Noise was injected deliberately to see if the algorithms could resist false patterns. The scientists were, in effect, running rehearsals with the data, ensuring that when the curtain lifted, the performance would not be an illusion. Error analysis became the mantra of the collaboration. Every step was scrutinized. Were the atmospheric corrections robust? Were the antenna calibrations accurate? Could instrumental noise masquerade as a ring? Entire subgroups devoted themselves to testing these questions, repeating analyses with different assumptions, swapping out parameters, cross-checking results. It was not enough to produce an image. They had to prove that the image was real. The importance of this rigor cannot be overstated. For decades, black holes had lived in the realm of theory. A single flawed image, rushed to announcement, could have damaged the credibility of the entire project. The world was waiting, and the scientists knew it. In April 2017, the data were taken. But it would not be until April 2019 that the image was revealed. Those 2 years were spent in cautious, methodical verification, ensuring that when humanity was shown a black hole, it was indeed a black hole and not a trick of noise. The process of imaging also revealed something poetic. In the visibilities, the shadow was not immediately visible. It existed only as patterns of correlation scattered across the Fourier plane. To the untrained eye, these patterns looked meaningless, dots on a plot. But to those who knew, they carried whispers of a circle, a ring hidden in the mathematics. To coax it into an image was to translate from one language to another, from the abstract grammar of Fourier transforms to the human language of pictures. When the independent teams finally compared notes, the results were astonishing. Each pipeline, though different in method, produced essentially the same structure: a bright ring, asymmetric, with a darker center. The size of the ring matched the predictions of general relativity almost perfectly. The asymmetry, brighter on one side, was consistent with relativistic beaming, plasma rushing toward Earth on one side of the disk, dimmed on the other as it receded. The shadow was there, not as noise, but as geometry revealed. And still, the scientists hesitated. They ran more tests, generated more synthetic data, explored alternative explanations. Could the ring be produced by something other than a black hole? The answer, again and again, was no. The simplest, most consistent interpretation was the one Einstein's equations had foretold a century earlier: a black hole, its event horizon casting a shadow larger than itself, surrounded by glowing plasma. It is easy, looking back, to take the image for granted: a blurry donut of light, orange against black. But behind that blur lay thousands of hours of computation, petabytes of data sifted through correlators, months of independent imaging, and relentless error analysis. The photograph was not a snapshot, casually captured. It was an edifice built from mathematics, patience, and discipline. There is something deeply human in this process. We are creatures of vision, drawn to images. Yet the universe does not always give us pictures easily. Sometimes it gives us patterns, correlations, whispers of structure in noise. To make an image, we must collaborate, test, and trust in both theory and method. The first picture of a black hole was not handed to us by the cosmos. It was coaxed, step by step, from data that resisted interpretation. And yet, the moment it appeared, the ring glowing on screens in conference rooms around the world, all the mathematics, all the caution, all the algorithms crystallized into something simple. A circle of fire around a shadow. Proof that darkness itself can be framed by light. The journey from data to image was as profound as the image itself. It showed that science is not only about collecting signals, but about translating them. It reminded us that the universe can be read in more than one language, that what looks like noise can, with enough patience, become revelation, and it demonstrated the power of humility, to test, to doubt, to verify, until no doubt remains. In the end, the correlators and algorithms did more than produce a picture. They transformed an absence into a presence, a shadow into a symbol, and in doing so, they gave humanity its first direct glimpse of the most elusive of cosmic actors. On the morning of April 10th, 2019, the world gathered to witness a scientific moment that had been centuries in the making. Press rooms filled in Washington, Brussels, Santiago, Taipei, Tokyo, and beyond. Cameras pointed at podiums, scientists waited nervously, and on screens concealed behind curtains glowed an image that no human had ever seen before. It was not sharp in the way of Hubble's deep-field galaxies or the crystalline arcs of Saturn's rings. It was not colorful like a nebula, nor filled with stars. It was, instead, a blurry circle, a ring of golden light, broken on one side, surrounding a dark center. Yet the meaning of that ring was staggering. It was the first direct glimpse of a black hole's shadow, the silhouette of an event horizon imprinted upon the sky. The subject was M87, the supermassive black hole at the heart of the galaxy Messier 87, some 55 million light-years away in the Virgo cluster. With a mass about 6.5 billion times that of the Sun, it was an object of incomprehensible scale, large enough to swallow our solar system whole. And yet, from Earth, its apparent size was tiny, about 40 microarc-seconds, equivalent to spotting a single grain of rice in New York from Paris. The feat of imaging it required a telescope the size of Earth itself, and that is precisely what the Event Horizon Telescope had built through VLBI. The image projected on screens that April morning showed a ring of emission about 42 microarc-seconds across, nearly perfectly circular, with a brightness asymmetry, the southern side glowing more intensely than the northern. This asymmetry was not an imperfection, but a prediction fulfilled. Relativistic beaming, an effect of plasma orbiting at near light speed, brightened the side moving toward Earth and dimmed the side moving away. The image was not only consistent with expectations, it was a visual confirmation of relativity's most exotic predictions. The size of the ring carried crucial information. According to general relativity, the diameter of the shadow should be about 2.6 times the Schwarzschild radius of the black hole. By measuring the angular size on the sky and combining it with the distance to M87, astronomers could infer the mass of the black hole with remarkable precision, about 6.5 plus or minus 0.7 billion solar masses. This value agreed beautifully with previous estimates derived from the motions of stars and gas in M87, lending confidence both to the measurement and to relativity itself. But the image did more than weigh a black hole. It probed the very fabric of space-time. For decades, physicists had sought tests of general relativity in the strong field regime, near horizons where gravity is most extreme. Einstein's equations had passed every test in the solar system, but those tests involved weak fields, Mercury's orbit, the bending of starlight during eclipses, the timing of pulsars. Near a black hole, the warping is orders of magnitude greater. If relativity were to fail, if quantum corrections or alternative theories of gravity were to emerge, it was here that deviations might appear. And yet, the ring was exactly where Einstein said it would be. Its circularity was within 10% of predictions. Its size matched the Schwarzschild solution to within uncertainties. Its asymmetry followed the logic of relativistic motion. Far from failing, general relativity triumphed again, extending its dominion into realms Einstein himself never dreamed would be observed. This success was not trivial. Alternative models of gravity had predicted different shadow sizes, different deviations from circularity. Some exotic theories, invoking modifications of relativity or extra dimensions, would have left fingerprints on the image. None were found. The result was not only a triumph for Einstein, but a narrowing of the landscape of possible theories. In the shadow of M87 star, entire classes of speculative physics dissolved. The announcement itself was as symbolic as the science. Scientists who had labored for years, often in obscurity, now stood before the world with their result. In Washington, Shepard Doleman, the director of the EHT project, unveiled the image with the simple words, "We have seen what we thought was unseeable." The phrase captured the paradox perfectly. A photograph of darkness, a shadow of an object that emits no light. Around the globe, the image spread instantly. Newspapers placed it on their front pages. Social media lit up with comparisons. To a fiery eye, to Tolkien's Eye of Sauron, to a cosmic donut. Memes flourished, jokes abounded. But beneath the humor was awe. Humanity had looked into the abyss and returned with a picture. Among the collaboration, the emotions ran deep. Years of work, thousands of hours of computation, countless late nights in observatories and labs had culminated in this ring of light. Some scientists wept, others smiled in quiet disbelief. Many described a sense of humility, of standing at a threshold larger than themselves. The black hole did not care that it was being photographed, but for us, the act was transformative. It is important to remember what the image was and what it was not. It was not a crisp photograph in the everyday sense, captured in a single exposure. It was a reconstruction, assembled from petabytes of data, processed through independent pipelines, tested against synthetic models. It was not artifice, but nor was it raw. It was the distilled truth of correlations, translated into human terms. The blur, the asymmetry, the glow, all were real, but revealed only through the lens of mathematics and computation. And yet, the power of the image lay precisely in its ordinariness. It looked like what physicists had predicted decades earlier. Jean-Pierre Luminet's hand-drawn simulation from 1979, shaded in ink by an early plotter, bore a striking resemblance. The ring was not a surprise, it was a confirmation, and in science, confirmation is often more profound than novelty. To see what you expect, in a realm where expectation itself feels impossible, is to affirm that your understanding of nature reaches into the abyss. The mass estimate of 6.5 billion suns also carried cosmic implications. Such a black hole could power the immense jet streaming from M87, a structure visible across millions of light-years. The image linked theory and observation, tying the small-scale dynamics of plasma near the horizon to the galaxy-scale fireworks of its jet. For the first time, the connection was not inferred, but seen. Physicists also noted the implications for the so-called no-hair theorem of black holes, the idea that these objects are characterized only by mass, charge, and spin. The shadow's size and shape suggested that M87 behaved exactly as a Kerr black hole should. There were no exotic departures, no hidden hair. The simplicity of Einstein's solution seemed to reign, even in the chaos of real astrophysics. In classrooms and lecture halls, the image became an instant teaching tool. For students learning relativity, the shadow was no longer an abstraction, no longer a diagram in a textbook. It was a real photograph, a bridge between mathematics and vision. For the public, it was an invitation into wonder, proof that science can make visible even the most invisible of things. But perhaps the most striking aspect of the April 10th announcement was the sense of collective achievement. More than 200 scientists, spread across continents, had contributed. No single person could claim the image. It was the result of collaboration at planetary scale, mirroring the very telescope that had made it possible. The Earth itself had become an eye, and humanity itself had become the observer. When the press conferences ended, when the applause faded and the headlines rotated, the image remained, a blurry ring, quiet and steady. It was the kind of picture that grows more profound the longer you look. At first glance, simple; at second, impossibly vast; by the third, philosophical, a photograph of darkness framed by light, proof that even the universe's shyest secrets can be coaxed into view. At the center of the Milky Way, hidden behind dense veils of stars, dust and gas, lies a monster that has shaped our galaxy for billions of years. It is not the largest black hole in the universe, nor the brightest, nor the easiest to study, but for us, it is the most personal. This is Sagittarius A, our home black hole, 4 million times the mass of the Sun, sitting quietly 26,000 light-years away in the constellation Sagittarius. For decades, its presence was inferred indirectly. Stars near the galactic center trace dizzying orbits, whipping around an unseen mass at speeds of thousands of kilometers per second. Observations by Reinhard Genzel's and Andrea Gheze's teams, painstakingly tracking stellar motions with adaptive optics, proved that a compact object of extraordinary density lurked there. In 2020, those discoveries earned them the Nobel Prize in Physics. The evidence was overwhelming. Nothing but a supermassive black hole could fit the bill. And yet, to see it directly was another matter. If M87 star was the giant of the Virgo cluster, radiating jets that blaze across intergalactic space, Sagittarius A star was the shy neighbor. Closer, yes, but more fickle, more elusive, harder to pin down. The irony is striking. SGR A star is more than 2,000 times smaller in mass than M87 star, but because it is so much closer, its apparent size on the sky is similar, about 50 microarcseconds compared to 42 for M87 star. In theory, this should make it just as accessible to the Event Horizon Telescope. In practice, it proved far trickier. The problem lay in timescales. M87 star is gargantuan. Plasma orbiting near its horizon takes days to complete a circuit. Its structure evolves slowly, almost statically, during the hours of an observing run. Sagittarius A star, by contrast, is petite on cosmic terms. Plasma whirls around it in mere minutes. Bright spots flare and fade, turbulence churns, magnetic fields snap and reconnect. By the time the Earth-sized telescope fills its Fourier plane, taking hours to collect enough baselines, the source has already changed. It is like trying to paint a portrait of a dancer while she is constantly spinning and shifting pose. This variability forced the collaboration to rethink its imaging strategies. Standard algorithms assumed the target was stable, its brightness distribution unchanging during the observation. For SGR A star, this was false. To cope, The EHT scientists generated not one image, but thousands, each consistent with different slices of the data. Then they averaged across them, producing a typical view of the shadow. The result was fuzzier than M87 star, less sharply defined, but unmistakable. A ring of light surrounding a dark center, just as relativity predicted. On May 12, 2022, the image of Sagittarius A star was revealed to the world. The announcement carried less surprise than the M87 image, for by then the technique was known, but it carried a deeper intimacy. This was our black hole, the anchor of the Milky Way, the quiet heart around which 100 billion stars revolve. To look at it was to look into the engine room of our own galaxy, the gravitational keystone holding the spiral together. The image showed a ring roughly 51 micro-arcseconds across, once again matching the predictions of general relativity. The asymmetry in brightness hinted at plasma flows, though the blurring from turbulence made details harder to discern. Still, the agreement with theory was clear. Like M87 star, Sagittarius A star behaved as a Kerr black hole should. No exotic deviations emerged, no cracks in Einstein's armor. The comparison between the two black holes revealed profound lessons. Despite their difference in mass, a factor of 1,600, both cast shadows of similar angular size. Both appeared as rings with darker centers. Both confirmed the same relativistic geometry. This universality was striking. Black holes, whether giants in distant galaxies or moderate monsters in our own, obeyed the same rules. Relativity, it seemed, cared not for scale. Yet their differences were just as instructive. M87 star, stable and immense, taught us about slow, large-scale accretion, the feeding of a behemoth that launches jets across intergalactic space. Sagittarius A star, restless and variable, offered a window into fast, turbulent accretion, the flickering plasma of a modest black hole whose hunger is more intermittent. Together, they provided bookends to the black hole family, one massive and steady, the other smaller and mercurial. The effort to image Jean-Pierre A star also highlighted the ingenuity of the collaboration. To cope with variability, they developed new methods of dynamic imaging, reconstructing movies of potential structures rather than static snapshots. These techniques will be crucial for the future, when the EHT seeks not only to photograph black holes, but to film them, capturing the swirl of plasma and the dance of light around horizons. For the public, the image of Sagittarius A star carried an emotional resonance. M87 star was impressive, yes, but it was distant, alien, another galaxy's heart. Jean-Pierre A star was home. It lay in the direction of the summer Milky Way, that hazy band arcing across the sky. When we look up on a clear night and see the dense star fields of Sagittarius, we are gazing unknowingly toward our black hole. The image released in 2022 transformed that abstract thought into something visible. This is what lurks behind the glow of our galaxy's center. This is the shadow within which our cosmic story unfolds. Astronomers, too, felt the weight of the moment. For decades, they had tracked the orbits of stars like S2, swooping near pericenter, slingshotting around an invisible mass. Now they could pair those stellar dances with a direct view of the shadow itself. Two lines of evidence, independent and converging, confirmed the same truth. Sagittarius, a star, is a black hole. There is no alternative explanation that fits. The implications stretched further. By measuring the shadow size, scientists could refine models of the black hole's mass, testing them against stellar dynamics. By analyzing the variability, they could probe the physics of accretion, the chaotic interplay of plasma and magnetic fields. By comparing Jean-Pierre A star to M87 star, they could ask whether black holes of different scales behave the same. And the answer, so far, is yes. And yet, the fuzziness of the image left tantalizing room for improvement. Future expansions of the EHT, with more telescopes and shorter wavelengths, may sharpen the picture, revealing details of the photon rings and the turbulent flows. Already, plans are underway for next-generation arrays, capable of producing not just stills, but movies of Jean-Pierre A star. To watch plasma orbit the horizon in real time, that is the dream now on the horizon. In many ways, Sagittarius A star is the black hole we feel in our bones. We orbit it, whether we think about it or not. Our galaxy is bound to it, our stars arranged around its pull. To photograph it was to bring home a truth we already lived within. When the EHT released the image, it was not just a scientific result, but a mirror held up to our galactic identity. This is where we are. This is the shadow at the center of our cosmic home. And so, with two images, M87 star in 2019 and Jean-Pierre A star in 2022, humanity crossed a threshold. Black holes, once theoretical oddities, then astrophysical suspects, became directly visible. Their shadows, carved in light, now sit in our catalogue of cosmic portraits, alongside the rings of Saturn, the spiral arms of galaxies, the filaments of the cosmic web. The unseeable had been seen twice, in two different guises. The triumph was not only in the pictures, but in the confirmation of universality. Black holes are real, and they look just as Einstein said they would. The image of M87 star, released in 2019, was breathtaking. The image of Sagittarius A star in 2022 was intimate. Yet in both cases, what we saw was only a still frame, a cosmic portrait frozen in time. The irony is that black holes are anything but still. The plasma that swirls around them flickers, churns, and evolves on timescales of minutes to days. Magnetic fields snap and reconnect. Bright spots orbit at near light speed. Turbulence ripples through accretion flows. The reality is dynamic, alive with motion. And so the next ambition, now taking shape, is to move beyond single snapshots. Astronomers want not only to photograph black holes, but to film them, to capture the shifting dance of plasma and light around horizons, to make movies of darkness framed by fire. This dream of time-resolved imaging has been present since the first planning stages of the Event Horizon Telescope. For Sagittarius A star, it is a necessity. Its smaller mass means orbital timescales are minutes, not days. The bright spots that appear in its accretion flow may orbit several times during a single night of observation. The image released in 2022 was an average, blurred by this variability. To truly understand it, we need not a single composite, but a sequence, a record of change. For M87 star, the timescales are slower, but the dynamics no less fascinating. Plasma clouds orbiting over days, shocks forming near the base of its jet, instabilities rippling outward. All of these leave fingerprints on the ring. A movie would show not only the existence of the shadow, but the choreography of matter at the edge of a singularity. Achieving this requires both technological and conceptual leaps. The current EHT, with its handful of telescopes, produces sparse coverage of Fourier space. Earth's rotation fills in more, but only slowly, over hours. To reconstruct rapid changes, more baselines are needed, more simultaneous samples, greater sensitivity. That is why the collaboration is expanding. New sites are being added to the array, telescopes in Africa, Greenland, and even planned installations in space. Each new station lengthens baselines, fills in gaps, sharpens resolution. The Atacama Large Millimeter/Submillimeter Array in Chile, already the crown jewel of the array, continues to provide unmatched sensitivity, but even ALMA cannot do it alone. The future demands a global orchestra, with more instruments playing together, their signals combined into sharper harmony. Hardware improvements are only part of the story. Algorithms, too, must evolve. Imaging dynamic sources is a different challenge from imaging static ones. The reconstruction pipelines must be able to follow changes over minutes, to distinguish real variability from noise, to track bright spots orbiting at relativistic speeds. New methods are being developed, Bayesian frameworks that incorporate models of accretion physics, machine learning tools trained on simulations, dynamic regularization that smooths across time as well as space. These tools aim not merely to make prettier pictures, but to capture reality in motion. Already, glimpses of this future are emerging. In 2018, using data from earlier campaigns, the EHT collaboration detected hints of hotspots orbiting Sagittarius A star, consistent with plasma circling the black hole in tens of minutes. More recent studies have tracked flares seen in infrared and X-ray by other observatories, correlating them with radio signatures. These multi-wavelength efforts suggest that black holes flicker like cosmic beacons, their light modulated by the dance of magnetized plasma near the horizon. To capture this flicker directly in images would be to witness relativity in motion. The scientific payoff would be immense. Movies of black holes would allow direct tests of orbital dynamics near the photon sphere. They would let us track the speed and brightness of plasma blobs, comparing them to models of magnetohydrodynamics. They would reveal whether turbulence follows the predictions of general relativity or whether anomalies emerge. And they might shed light on how black holes launch their powerful jets, the mechanisms that accelerate matter from the chaos near the horizon into streams spanning thousands of light years. But there is also a philosophical allure. A single photograph is powerful, but it feels static, almost timeless. A movie, by contrast, breathes. It shows becoming, not just being. To watch a black hole's surroundings evolve would be to feel, viscerally, that these objects are not abstract. They are alive with motion, constantly reshaping themselves, pulsing with energy. The universe would no longer be frozen in a single frame. It would unfold before us, moment by moment. There are challenges ahead. Atmospheric noise remains a formidable foe, especially at shorter wavelengths where sharper resolution beckons. Data volumes will grow even larger, petabytes swelling into exabytes, demanding new strategies for storage and processing. Calibration will become more complex, for errors can masquerade as variability. The collaboration will need to disentangle what is real from what is artifact, with even greater rigor than before. Yet, the trajectory is clear. Just as the first image of a black hole once seemed impossible, so too does the idea of a movie now seem ambitious. But technology marches, algorithms improve, collaborations expand. Already, next-generation projects are on the horizon. The NGEHT, Next Generation Event Horizon Telescope, with more sites, greater sensitivity, faster data rates. With it, time-resolved imaging will move from dream to practice. Space, too, beckons. Adding radio dishes in orbit, on satellites or even on the Moon, would extend baselines beyond Earth's diameter, sharpening resolution by orders of magnitude. Such instruments could, in principle, capture not only the main shadow, but the delicate photon rings, nested circles formed by light looping multiple times around the black hole before escaping. To watch these rings flicker in real time would be to see the very geometry of space-time drawn in motion. As these ambitions take shape, one cannot help but reflect on the arc of progress. In 1979, Jean-Pierre Luminet drew the first simulated image of a black hole by hand, his plotter shading pixels from numbers on punch cards. 40 years later, the EHT unveiled the first real photograph. 40 years hence, we may have movies of plasma orbiting horizons, photon rings captured in motion, turbulence traced as it dances across the brink of eternity. The path forward is not just scientific, but symbolic. Movies humanize the abstract. They turn equations into experiences, diagrams into stories. To watch a black hole flicker and flare would be to feel in our bones the truth of relativity, not just as mathematics, but as spectacle. It would be science as cinema, nature writing its own films in the light of plasma and the curvature of space-time. And perhaps, when the first movie is finally shown, the moment will echo the unveiling of the first still image. The world will gather again, scientists will stand again before cameras, and on screens will play a short flickering sequence, a ring of fire brightening, dimming, shifting, alive with motion. And in that flicker, we will see not only a black hole, but our own persistence, the human refusal to accept invisibility, the determination to watch even the unwatchable. The shadow, once a static silhouette, will become a living dance, and humanity, once more, will have turned impossibility into vision. When the first image of a black hole appeared before the world in April 2019, and again when the portrait of Sagittarius A star was released in 2022, something subtle happened. People looked, blinked, and said, "Is that it? A fuzzy ring, orange against black, hardly the dazzling spectacle of a galaxy or nebula." But then, slowly, the realization seeped in. This was not just a picture. This was a paradox captured in pixels. It was the act of seeing something that cannot, by definition, be seen. What does it mean to see darkness? The question is as philosophical as it is scientific. Shadows are normally the absence of light cast by presence. They tell us something is there because light refuses to pass. The shadow of a black hole, however, is stranger. It is not cast onto any surface. It is not an absence projected, but an absence itself, outlined by the swirl of light around it. To see such a shadow is to witness geometry revealed, not matter. It is to see the silence of space-time made visible through contrast. This raises the deeper question of perception. When we gaze at a black hole image, what are we really looking at? Not the singularity, not the event horizon itself, which forever conceals what lies inside. We are seeing the threshold, the boundary where light falters. It is a reminder that our knowledge of the universe is always mediated by photons, by instruments, by algorithms, by interpretation. To see a black hole is not to look directly into the abyss, but to look at how the abyss shapes what surrounds it. It is vision by proxy, presence by absence. And yet, in this proxy lies profound truth. The size of the shadow tells us the black hole's mass. The asymmetry in brightness tells us about motion and plasma flows. The very existence of the ring affirms relativity's predictions. It is a shadow that speaks. But the shadow also keeps secrets. At the heart of every black hole lies the singularity, or so the equations say. A point where density becomes infinite, curvature unbounded, the laws of physics collapse into silence. Do singularities truly exist, or do they mark the edge of our understanding, where quantum gravity must take over? No image can answer that. The shadow draws a veil across the ultimate mystery. And then there is the information paradox. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects allow them to emit a faint radiation, now known as Hawking radiation. Over unimaginable timescales, this would cause black holes to evaporate. But the radiation, as he first described it, carried no imprint of what had fallen in. If true, information would be destroyed, lost forever to the universe. And yet, quantum theory insists that information is never lost. The paradox has haunted physics for decades, unresolved despite oceans of papers and debate. Does information escape, encoded somehow in subtle correlations of Hawking radiation? Does it linger on the horizon in soft hair, as some propose? Or does the interior hold answers that defy our current mathematics? The shadow gives no clues. It shows us the horizon, but not what it conceals. Other puzzles linger. Do black holes obey relativity exactly, or are there tiny deviations waiting to be found in photon rings? Does quantum gravity, the sought-after union of relativity and quantum mechanics, reveal itself near horizons? Are black holes gateways to other regions of space-time, or are they ultimate dead ends? Each question is sharpened by the images, yet none are answered fully. The photographs are both revelations and reminders of ignorance. Future telescopes promise to push deeper. The next generation Event Horizon Telescope, with more sights on Earth, will sharpen resolution, filling in the gaps in Fourier space. Space-based VLBI, with radio dishes in orbit or even on the Moon, could extend baselines beyond Earth's diameter, revealing details invisible today. These instruments might capture the nested photon rings, the delicate structures predicted by theory. They might resolve turbulence in accretion flows, track hotspots as they orbit, even film the evolution of black holes in real time. There are also dreams of multi-wavelength synergy. Pairing millimeter images with X-ray and infrared observations could give a fuller picture of black hole environments, each band tracing different layers of plasma and magnetic fields. Gravitational wave observatories, too, are part of the story. Where the EHT shows shadows, detectors like LIGO, VIRGO, and the future LISA mission reveal the ripples black holes send through spacetime when they merge. Together, images and waves create a fuller portrait, not only how black holes look, but how they move, collide, and echo through the cosmos. And as we look ahead, the symbolism deepens. To photograph a black hole is to confront the limits of human perception and ingenuity. It is to take the most elusive object imaginable and insist, "We will see you." It is an act of defiance against invisibility, but also an act of humility. For even when we succeed, what we see is not the whole, but the outline. We are reminded that the universe keeps some truths hidden, that knowledge always has horizons. The photographs also speak to something broader, our relationship with darkness. In art and literature, darkness is often a metaphor for ignorance, fear, or the unknown. But here, darkness becomes a source of knowledge. By imaging the shadow of a black hole, we learn not only about the black hole itself, but about the laws of physics at their most extreme. Darkness becomes data. The absence becomes signal. There is a strange comfort in that. The universe is vast and often indifferent, but it is not incomprehensible. Even its shadows can be studied, quantified, turned into knowledge. We may never see the singularity, but we can trace its influence. We may never escape an event horizon, but we can measure its size. The abyss may not speak, but it can be photographed. One day, future telescopes may sharpen the shadows into finer detail. Perhaps they will film Sagittarius A star flickering in real time, or resolve photon rings orbiting like concentric halos. Perhaps they will show turbulence in plasma streams or the footprints of new physics. Each step will peel back a layer, yet the core mystery will remain. What lies inside? And maybe that is the point. Science thrives not only on answers, but on the persistence of questions. To see a black hole's shadow is not to close a chapter, but to open new ones, each deeper and more subtle. The photographs are milestones, but not endpoints. They are thresholds, reminding us that discovery is always unfinished. Standing before the image of M87, or Sagittarius A, we are confronted with a paradox that is as poetic as it is scientific. We have seen darkness. We have turned absence into presence. We have looked into the abyss and brought back a picture. And in that act, we have seen ourselves, our curiosity, our patience, our need to push against horizons, to capture even the shadows of the unseeable. The future will bring sharper images, dynamic movies, space-based telescopes, and new physics. But even now, with two blurry rings, we have crossed a profound threshold. For the first time in history, humanity has looked directly at the edge of nothing and found that even nothing casts a shadow. And so we drift back from the edge of the abyss, from equations scribbled centuries ago, to radio dishes listening across continents, to images that turned shadows into presence. We've followed the story of how humanity managed to photograph darkness itself. What lingers is not only the science, but the feeling. That even in the vastness, even in the silence of black holes, there are ways to listen, to see, to understand. That absence can become signal. That mystery itself has shape. If you're still awake, I hope you carry with you a sense of wonder, a reminder that curiosity is patient, persistent, and endlessly creative. And if you've drifted to sleep somewhere along the way, may your dreams be gentle, lit with rings of fire circling silence. Thank you for joining me. Rest well.